Hey everybody, in this video we will be going over three examples related to the binomial distribution, and here is the first example. The probability that a patient recovers from a stomach disease is 80%, and suppose there are 20 people that are known to have contracted this disease. Remember, a patient recovering, the probability of a single patient recovering is 80%. What is the probability that A, exactly 14 of these 20 people recover, B, at least 10 of these 20 people recover, at least 14 but not more than 18 people recover, and at most 16 people recover? Alright, so let's just go ahead and solution 1. So we have 4 parts, A, B, C, and D. Oh, why did it work again? Okay, let's do it again. Oh, I think I know why. C. Okay, and finally D, part D. All right, so we have 4 parts to that question. And let me just go ahead and align them. Control X. There you go. All right, so for the first part, exactly 14 recover. So the probability that the number of people who recover is exactly equal to 14. Okay, so because we have 20 people in the population, let me first write out the open formula for that. So you guys can imagine it will be 20 choose, let me write that down, 20 choose 14, and the closed form formula times. So we want 14 of these people to recover among those 20. There are 20 choose 14 ways to figure out those 14 that will recover. So many different ways to figure out which 14 will recover, and because the probability of recovery for an individual person is 80%, so 0.8 close parenthesis raised to the power 14, and then times 0.2, the probability of not recovering, raised to the power 6. 6 people will get 6. So that is the formula that we will be using. All right, so let me just go ahead and go right inside the formula, do a couple of modifications here. Let me put parentheses here because I want to avoid any error. I don't want any error here. There you go. And finally, the part which I need to really make a modification is this part, 20 choose 14. In Excel, you do combine. Oops. First, let's put the equal sign at the beginning. Now Excel will understand this is a formula. So you write combination. There you go. And it's 20 number. We want to, from among 20 numbers, we want to choose 14 of them. And that's it. So that basically gives us the formula that we needed. So 10.91% of the chance that exactly 14 people will recover. Now we could have done an alternative solution here, or alternatively we could have directly used the binomial formula that is already available in Excel. So let me just go ahead and show where that formula can be found. Formulas. So you can either go to statistics and the binomial dist formula. Usually that's the way I find it. So let me just use that one. So you can see the dialog box. So on the dialog box, the number of successes 14. The number of trials 20. From among the 20 patients, we want 14 of them to be to figure out the probability that 14 of them will be recovering. The probability of individual successes is 80%, 0.8, maybe I can put a 0 there, and that's it. Is it a cumulative one or individual? We need to write a true or a false. Actually, by skipping it, the default I think is false, if I'm not mistaken. But if you want a cumulative probability, we'll just solve a couple of problems where we'll use cumulative. But this one says exactly 14, so this would be false because it says exactly. And that's it. Press OK, and boom, 10.91. So 0.1091 is the probability. So you can either come up with your own formula, write it the long form, or directly use the built-in Excel function to do that. All right, second question, at least 10 people recover. So the probability that X is greater than or equal to, greater than or equal to 10. So what is the probability that 10 people will recover? Well, let me just go ahead and do that. All right, so for at least 10 people to recover, there's multiple ways we can imagine. So that means we want 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All those, we want to add them. We want to find those probabilities and we want to add them. Well, there's two ways we can do it. Either we can build a table, which I'm about to do next, or we can just directly use the binomial dist formula. Let me just show you in both ways. Binomial dist is obviously the fastest way, so you probably should learn how to use binomial dist. So number of successes is 10. Number of trials is 20. Probability of success is 0.8. And okay, so when it says cumulative, if I say true, what it does is that cumulative is all the way up to 10. The probabilities of all the way. So the probability that no one will be successful, one person will be successful, two person, three person. I mean, when I say successful, three person will be healed, will be cured by that drug or whatever we are using, or maybe just and the probability that the patient will recover, right? So, but if I use it in this form, it is 10 or less. Does that make sense? So binomial dist, when you use it with the cumulative true, it gives you the number or less. The number or less. So basic, but because I want 10 or more, not 10 or less, so what should I do? Well, there's a couple of different ways you can do it. Why don't I find 9 or less? So let's just change this to a 9 and subtract it from 1. Do you see that? We call this complementary counting. So here what this will give me is 9 people, 8 people, 7, 6, 5, 4, 3, 2, 1, 0 people recovering. And if I subtract those recoveries from 1, it will give me 10 or above. So the binomial dist here is 9 or less. If I subtract it from 100%, it will give me 10 or more. Press enter. Okay, so I'm claiming that's the answer. Let me write it in percentages. Probably it's better. And adding more decimal place. There you go. 99.94% will be, okay, so this, oh yeah, it makes sense. 99.94% will recover. So 99.94% of the patients, 99.94% is the probability that either 10 people or 11 people or 12 or 13 or 14 or 15, 16, 17, 18, 19 or 20 people will recover. The probability that 10 or above people from among those 20 patients will recover. So therefore, the probability that 9 or less people will recover will be 0.06%. All right, so if you didn't recognize this, alternatively, what we could have done is the following. X number of people who recover, because the question says at least 10, X equals 10, X equals 11, and so on. X equals 12. So we want to see, find out all of these, right? So, and so on. You know what I will do? I will directly put something on top. Let's just say X here. So then 10, 11. So it will be easier just to write the numbers here. All the way up to 20. And here are the individual probabilities. All right, so binomial dist. I'm not gonna even bother writing the formula. Number of successes is this number from among 20 people, and probability of success is 0.8, and that's it. This one is a false. I don't want to use cumulative. I already used cumulative. I already know the answer, right? I'm trying to solve it without using cumulative distribution. There you go. Double click, sum them up. Sum equals. You can just directly say alt equal. Oh, sorry. Alt. So it doesn't work. Okay, so fine. Oh, I forgot to put the equal sign. Okay, there we go. Alt equal. Okay, it doesn't work. All right, fine. Okay, so somehow it doesn't work. So let me just write the actual formula. Sum all these probabilities, basically. Close parenthesis. Hey, look at that. So these are exactly the same numbers. Perfect. So in this exercise, at least we learned the cumulative probability, right? So that was pretty cool. For part C now, at least 14, but not more than 18 people will recover. X, so it's asking for the probability that it will be between 14, I should say, 14 less than or equal to X less than or equal to 18. Does that make sense? That's what the question asking. So make sure you understand what the question, the wording is. So we want the number of recoveries. X is the number of recoveries. Maybe I should have mentioned this earlier here. X is, let X be the number of recoveries. There we go, given that. All right, so at least 14, X is at least 14, but no more than 18. So we want this range. So let's try to figure, so basically the question is asking for the sum of these numbers, right? That's it. That would just solve the problem. So let's solve it in two different ways again. The sum of from 14 all the way to 18. So that's one way to solve the problem. 84.41%. Let me just write it as a percentage. There you go. Alternatively, now this is the alternative, or alternatively, we could have done this. We could have used the cumulative distribution. So this is something we want to practice on, right? So that would have been equal to, so check this out. So it's as if we want less than or 18, X being less than 18. Let me write it over here. So it looks like this is the same thing as probability that X is less than or equal to 18. From those, subtract the probability that X is less than or equal to 13. Does that make sense? Because those that are number of recoveries being less than or equal to 18, 17, 16, 15, 14, 13, 12, if you subtract those which are less than or equal to 13, what will remain will be those that are between 18 and 14. I hope that's clear. All right, so let me just do this. So therefore, we will use cumulative distribution twice. Binomial dist, number of successes is 18 out of 20. Probability of success is 0.8, and then this one is a true. From that, we want to subtract a new binomial dist. Number of successes 13 this time, I should say 13 out of 20. Probability of success 0.8, and again true. That's it, and there you go. So it's basically the same probability. So pretty good. So it's important to learn the probability theory overall, because in business everything is probabilistic. The future is uncertain, right? So it's a risky future, and we want to make sense of the future. We want to somehow quantify it. So that's why this is very, very important. So why binomial distribution in particular? Because it's easy to model the unknown future with a binomial distribution. This is the easiest uncertainty that you can imagine. Is tomorrow going to rain or not? Is tomorrow, will we have more than 100 customers or less than 100 customers? Will tomorrow, so you can ask pretty much any question, yes, no type of questions. If it's yes, no, true, false type of questions, that's a binomial distribution. As long as you ask enough questions, you should be able to, what do you call it? Model the future, the unknown future, as much as you want. Obviously, it doesn't have to be efficient. Usually it is not. So you want to find the most explicit distribution possible, but at least you have an idea what's going on here, right? Awesome. So D finally, at most 16 recover. At most 16 means 0 people, 1 person, 2 person, all the way up to 15%, 16% recover. So this is easy. So this is probability that X is less than or equal to 16. Right, so that's what the question is asking. Let me just move it. This is just a cumulative distribution, right? So we've done this before. So that's just a direct cumulative distribution. Binomial dist, number of successes is 16 or less, right? So 0.8, true. I hope that's clear. There you go. 58% of the individuals will be let me put a percent sign here and this. All right, 58.86% of the people will be recovering from that. Let me check my notes. Perfect. So second example, a multiple choice exam has 15 questions, which each with 5 possible choices. So it's an A, B, C, D, E type of exam. And suppose there's someone, a student, who has no clue about the questions. He's just going to randomly, independently guess each question, right? We will try to guess the answers to each question, 15 of them. What is the probability that this student will guess at least 10 of the 15 questions correctly? 10 questions correctly by this student who will go ahead and guess. Just for the record, I want to clarify on something. What is the most likely, if you keep guessing, in average, how many questions do you think this student will get right? If he guessed all the answers, in average, what is the most likely scenario? Well, you might imagine the most likely scenario is that because he has only 20% chance of being right on any question, and because there are 15 questions, 15 times 20%, that's the mean of the binomial distribution, by the way. Let me write that down just for those of you who has never seen this before. So the mean of the binomial distribution is found by the sample size, if you want, times, this is the size of the whole thing, times the individual probability. So that will give you the mean. The standard deviation, on the other hand, oops, let me just do it over here. It would be just n times probability of success times q. Sometimes they write probability of failure as q. I usually prefer 1 minus p, right? Because we know that there are, if the probability of success is p, probability of failure will always obviously be 1 minus p. Oh, and then the square root of all this. Oh, shoot. Okay, so how did I mess this up? Okay, hold on. The square root of all this. Square root of all this. There we go. If without square root, it would be the variance. So that in general is the mean and the standard deviation of a random variable which has a binomial distribution, a binomial random variable. All right, a binomial random variable where there are n trials. Probability of success of an individual trial is p. Probability of failure as a result is 1 minus p. What is the mean? Well, in average, how many successes will we get? Right, so therefore we are expecting 15 times 0.2, 3 questions in average he will get right. And we are asking if that this student is expected to have 3 questions right. We want to find the probability that he will get 10 questions right. So it has to be an extremely small probability. All right, I will solve this in 2 different ways. So if that let's call it y, for instance, the random variable is y. Y is the random variable associated with the number of correct questions. Let y be number of correct questions from 15 trials. Oops. So we have from 15 trials. So if you want, let y be the number of successes from among 15 trials, or let y be the number of correct questions from among 15 questions. So the questions, the individual questions, are the trials. Does that make sense? All right. So yeah, this is annoying. Okay, let me just move this to the side now that we answered all those questions. Okay, good. All right, so basically what I will do is pretty much solve it in 2 different ways. Y equals 10, 11, 12, 13, 14, 15, right? Let me actually move the whole question down a little bit, right? So it might make sense. Okay, there we go. Control X, enter. All right, we just shifted the question down. As a result, we need to also shift question 3 done, right? Yeah, it's not gonna nice. Okay, question 3 is done too. Perfect. Now there's more space to work with the problems. Control X. All right. And the probability of Y having exactly solved the students having solved exactly 10 questions. So that's just binomial dist. Number of successes is that number. Out of 15 questions, the probability of success is 0.2, and we want this false. We will solve this question with the cumulative as well in just a minute. And then we will just drag this down and add them up. So this one is the sum. So because the question says the probability that he will have at least 10 questions correct means 10 questions or 11, 12, 13, 14, 15 questions right, or 10 or 11 or 12 and so on. So this is sum of all these numbers. There you go. So it's a very, very, very tiny probability. Let me write it as a percentage. It is 0.01%. If you want one more decimal, 0.011%. It's tiny probability. Alternatively, or we could have done this. We could have used the binomial dist formula with the true cumulative probability. So the cumulative probability will give me 10 or more. No, it will give me 10 or less. So what I can do is from 100%, I can subtract 9 or less successes. That will give me the complementary probability, which is 10 or more successes. Does that make sense? From 1, if I subtract 9 or less, the outcome will be 10 or more. So that's equal to 1 minus binomial this. Number of successes 9 out of 15. Probability of success is 0.2. And this time I'm going to write true here. Does that make sense? Not false anymore. And boom, the same answer. All right, so let's just put %sign here. One more. Okay, so how about this? Let's put this one also one more decimal, please. So it is, I mean, it is tiny. It's 1% of 1%, right? So something like that, in that order. So here we use cumulative, or you can use the table. Usually until you get really convenient with using complementary probabilities and cumulative distributions, I highly recommend the table. So the table will give you the whole picture, and then you can select from the table the pieces that you want. So finally, this one, question 3, last example. A new surgical procedure is successful when a probability of with a probability of P. Assume that the operation is performed 5 times on 5 different patients, and the results are independent of one another. So the 5 patients are not related in any sense. They are not relatives, whatever. So sorry for that. What is the probability that, so we have 3 questions now, so let's have them here. A, B, C. All right, so what is the probability that, let's call the random variable W, I guess. So W is, so for the first question, all 5 are successful. W is equal to 5. All right, so what is W again? Let W be the number of successes. In this example, an operation which is successful. Okay, number of successful operations. Operations in how many trials? In 5 trials. 5 trials. So we have 5 operations. So first question, what are the chances all 5 are successful? Given that P is equal to 0.8, given that an individual operation being successful is very high, 80%, what are the chances that all 5 are successful? Even though a single operation being successful is very high, 80%, all 5 being successful is somewhat unlikely. Or let me say less likely. All right, so this is binomial dist again. Binomial dist. Number of successes 5, number of trials 5. Given the probability of success is 8, and this one is not a cumulative distribution, just false. There you go. Wow, 32% chance. So even though the probability that a single operation will be successful is 80%, pretty high, all 5 of them are being successful is less than a third. So less than 33%, right? So which is kind of worrisome. Next one, exactly 4 are successful. So the probability that W is exactly equal to 4. So basically the same thing, right? Equals binom.dist. The only difference here is 4 successes from out of 5. The probability of individual success is now 60%. If the operation is known to not be as good as we used to think, so if the probability of success for an individual operation is 60%, what's the probability exactly 4 of them will be successful? 25%, 25.92%. Let's put the percent sign here. There you go. And finally, well, how would we could have used the formula again, just for those of you, if you want to use the formula. This is really combine. I mean, it is annoying, right? So I wouldn't recommend using this times. It's very likely you will make an error if you do it like this. The probability of individual success out of how many operations? Sorry, 4 of them successful times failure, and we want exactly 1 of them to be failed. So that's it. Yes, that's the same answer. All right, finally, last question. Less than 2 are successful. So the probability that W is less than or equal to less than 2. Sorry, not less than or equal to, strictly less than 2. What does that mean? That means 0 or 1 successes, given that P is, the probability of success is very small. So this number will come up big, right? Because the probability of success is small on an individual operation. So you can imagine just 1 or 2 patients will be healed, if at all. So therefore, this number is probably going to be high. I'm going to solve this in 3 different ways. Binom dist. Number of successes, well, because we want less than 2, either 0 from among the 5 operations, given that the probability of success is slim, this is false, plus binom dist, the number of successes is 1 from among the 5, so 0 or 1 basically. So that's what I'm doing, and this is false. Does that make sense? Press enter. That's it. That's the desired probability. 52.82% chance we'll have less than 2 patients will recover if the chances of success in any given operation is 0.3%, which means, I mean 0.3, which is 30%. Now, I kept using the same convention, but just for the record, the 0.3 is the same thing as 30%, right? I'm assuming you guys learned it in your college algebra courses, right? Let me just edit here. So those 2 numbers are the same thing, 0.30. So how do you translate a decimal into a percent? You divide it, you multiply it by by 100, and you put a percent sign next to it. So for instance, 0.35, that would be equal to, just multiply by 100, so that would be 35, and put a percent sign. There you go. How about, for instance, a more harder one? For instance, this number. What percent is this number equal to? Easy. Just move the decimal place 2 places. So it will be 0.0056, 0.0056, and then put a percent sign next to it. Oops. It automatically converted it. All right, it's the same thing. Yeah. All right, so let's put that thing. All right, so those are the same things. Okay, awesome. Yeah, we found the answer basically by adding 2 binom dists, as you can see in the formula. Alternatively, we could have used the cumulative distribution, but because cumulative distribution uses less than or equal to, for this one, the cumulative distribution, if I want to use it, I want to make it less than or equal to 1, right? So binom dist, because either 0 or 1, less than or equal to 1, because it says strictly less than 2, right? So 1, comma, out of 5 trials, probability of success is 0.3, and this one is a true. So true means it makes it cumulative, and that's the same answer. Lastly, you can construct the table. Okay, I'm not gonna go there. All right, so you guys can construct the table if you want. That's pretty much it. So hope you guys enjoyed these 3 examples, and it was useful in terms of having seen some applications, and looking forward to see you guys in our next lecture.